So as promised, from today we are going to study voltage control oscillators. Okay. So we looked at mixers where you need the LO signal, and the LO signal is actually generated from a voltage control oscillator which is locked through a phase lock loop. Okay, so that will look something like this. So you have a good reference which is a crystal oscillator. You have a let's do a PFT, a charge pump. You have a loop filter, and then the oscillator which produces the LO output, or some multiple of the LO, or some either multiple or maybe even a subharmonic of the LO. And then that frequency is divided and phase is divided down by some number n and fed back to the PFT. So the PFT basically tries to frequency and phase lock this output. So let's call this FDiv to Fin. Okay, so this is a negative feedback loop which tries to set those two to be equal. So once your FDiv is set, your FVCO is also set, phase and frequency. Okay. So that is one major application, which is to select, let's say, to perform the local oscillator function in mixers, in RF transceivers. Okay. Okay. So what are other functions? So you could have clock and data recovery circuits in optical communications. Okay, where your signal is sent as some series of zeros and ones, and you want to generate the frequency directly from the transmitted signal itself, from the received signal itself, as well as get the data in terms of zeros and ones through the transitions. CDRs, clock, and which one? CP is charge pump. Okay, so what happens is this, like I said, this PFD sets these two things, this whole loop sets these two frequencies and phases to be equal. So what this PFD does is it compares your input phases and input frequencies and produces a proportional output. Okay, and that is converted by the charge pump into a proportional current. Okay, and that current, the high frequency component is filtered out, and this produces a DC, some DC control voltage, VDC. Okay. Of course, the other place where you would need VCOs and PLLs are in microprocessors, where you need to create the clocks for the microprocessors, and quite often you might need to synchronize different systems. Okay, so you would use PLLs there again. So what are the different types of oscillators? So one kind is relaxation oscillators. Okay. So the main problem with these is that they are too noisy. Okay, and in other words, they are not spectrally pure enough. So remember, your LO signal ideally you want it to be a delta function, right? A pure cosine. And unfortunately, these types of oscillators have the noise is too high to be useful in RF transceivers. Okay, so we are not going to concentrate on them. The other kind are the harmonic oscillators. Okay, so these usually depend on some kind of harmonic filtering. Okay, harmonic filtering as in some kind of LC kind of circuit. Okay, so these are the most popular oscillators used in RF transceivers. Now, if you have other applications like microprocessors or maybe even CDRs, you could make a case for, let's say, ring oscillator based PLLs, but typically in RF circuits even ring oscillators are not very common, okay, because the noise levels are too high. Okay, so if you have seen, so they depend on some kind of charging and discharging cycle. Let me see if I remember the something like this. Okay, this is a very simple example, but basically what happens is this is a positive feedback circuit. Okay, so what happens is this current keeps switching between the two sides. So at any time, because of the positive feedback, one of these two sides will be on, the other side is turned off. Okay, so what happens is at any time, these two are obviously current sources. So it's, let's say this one is on, right? So you have current flowing like this and you have current flowing like this. Okay, so the capacitor gets charged in one direction. Okay, in the other half cycle, the current flows through the capacitor in the opposite direction. Okay, and it's a constant current charging the capacitor. So if you look at the voltage across the capacitor, it look like this. It look like a triangular wave. And if you actually look at the output, it look like a square wave. Okay, this is one example of a relaxation oscillator. It's called a relaxation because your capacitance charges till a certain point. As the capacitance charges, okay, the voltage at one end obviously goes up because it's charging through the current. And let's say this one is on, right? So this current is flowing like this. So the voltage at this end keeps increasing till it turns this guy off, and it's enough to turn on this guy. Right? This is a simple example of a relaxation oscillator. Sorry? Phase noise. Yes. We will come to it next class. Okay, we'll come to, actually I didn't even mention phase noise. So, oh, did I mention phase noise? I should have just said noise, but okay, we will come to what phase noise is next class. Okay, maybe next class or the class after that. We'll definitely be covering it. It's extremely important, okay, for VCOs. So we will come to phase noise. I just wanted to say noise. Obviously I let out the phase portion. So we'll come to it next class or the class after that. Okay. Now you would have all studied in some undergraduate course, right? Most probably your first level undergraduate course about a very simple feedback model for an oscillator. Okay, what are the conditions for for oscillation, right? So let us just take a system H of S, okay, where the output is fed back to the input. Y of S by H of X of S H of S by 1 minus H of S, right? Okay. So what do we know? If you have H of S equals 1, okay, implies that you can have a Y of S with no X of S input. Okay. Sorry. So HFS equal to 1 is the condition for oscillation. I think you guys must remember this, right? Okay, so these are called the Barkhausen criterion. You've heard of these, right? Heard of this name, Barkhausen? So in other words, sorry. Okay, so the amplitude should be 1 and the angle should be 360 degrees. Okay, and these are both valid at S equals j omega naught, where omega naught is the oscillation frequency. Okay, now the other thing you should know is, remember is, this 360 degrees is the total phase shift. In many circuits, you will have some kind of DC negative feedback, okay, which means you already have 180 degrees of phase shift at DC and you have to add an excess phase shift of another 180 degrees to bring it to 360 degrees for oscillations, okay. Sorry. So if you look at most RF oscillators, they implement something like this, except they also add an RLC network here. It's a frequency selective network, okay, which helps to set the frequency of oscillation. Okay, so what you'll find is the RLC network helps to, so we know that the RLC network has very low impedance, okay, at all other frequencies. Let's say a parallel RLC network, it has very low impedance at all other frequencies except at resonance where it has high impedance. Okay, we are going to use that property to create the oscillator, and most RF circuits end up using something similar to this, okay, this kind of property. But remember your Barkhausen criterion, okay, they are only necessary conditions, they are not sufficient conditions. Okay, in other words, if you have oscillations, you necessarily have to have these conditions satisfied, but if these conditions are satisfied, it doesn't mean you need to have oscillations. I'll give you a very simple example. Okay, let's take the case of this guy. Okay, this is a very simple example of you have enough loop gain, you have enough phase shift, but we know that the circuit is going to latch up. Okay, it's a 4-stage ring oscillator, you know it's not going to oscillate. Okay, so what we'll do is we'll take some simple circuits and see whether conditions are satisfied or not, and come up with a case where condition is satisfied for oscillation. Yes.
If mod of H is equal to 1, and the phase shift is 360 degrees, then it is a oscillator.
No, not necessary. It's not actually, it's not a necessary condition for oscillation. Sorry, it's not a sufficient condition for oscillation.
Gain is more than 1, then you cannot say it is necessary.
Which is why I said the conditions are gain equals 1 and phase shift equals 360 degrees. Those are the necessary conditions for steady state oscillations, right? But if those are satisfied, I can give you a circuit which does not. I can show you several circuits. In fact, you will see why it's a necessary but not sufficient condition. Okay, we'll come to that. You'll understand that a little bit better once we go through this, hopefully by the end of today's class. Okay. So does this circuit oscillate or not? Definitely does not, right? Why? You have a DC phase shift of 180 degrees, and then the RC gives phase shift between 0 to 90 degrees. So you can never get 360 degrees phase shift, right? Okay. So the maximum phase shift you have is 270 degrees, right, at infinity. Okay. So we know we don't have enough phase shift for this circuit. So let's try to help it a little bit. Sorry. Okay, how about this guy? First of all, your DC shift is 360 degrees. Okay, so that itself shows you the circuit is going to latch up, right, one way or the other way. Okay, what is the excess phase shift? It's between 0 to 180 degrees, right? So you know definitely the circuit will not oscillate. Okay, so now we know the problem. Let's say in these two cases the problem was with the phase shift. Okay, so let's try to help, and obviously the DC phase shift is 360 degrees. So what we'll do is, next we'll try to add an ideal inverter. Okay, so does this circuit oscillate? Why not? Right? Only at infinity you will get 360 degrees. Because inverter is ideal. Okay. How about this guy? Will it oscillate? It could oscillate, definitely. Okay. Okay, so let's try to find out what the frequency of oscillation is first. So first of all, at DC you have 180 degree phase shift, you know that, around the loop. Okay, let's say for each stage your input by output is minus A naught, which is the gain, right, which is GMR in this case. This is the gain of each stage. Omega p, let's neglect the capacitance of the transistor and so on. So it's 1 over RC, right? So what is the loop gain HFS? It's minus of A naught over 1 plus S by omega p whole cube. right? Okay, so let's say you're going to plot h of mod of h of j omega and angle of h of j omega. So the DC gain is going to be GMR the whole cubed, right? You have 3 poles at 1 over RC, so it goes at minus 60 dB per decade after this, right? Okay, and so let's plot the angle. So to start off with 180 degrees. Okay. Actually, let me draw it a little bit. Okay. And at let's say okay, so this is minus 90 degrees, right? The final phase. Okay, so the total phase added is from each one of the blocks. Okay, and you of course have 3 poles at 1 over RC. What is the excess phase added at omega equals 1 over RC? It's 3 into 45 degrees, right? You know that. So let's say omega naught is the frequency of oscillation. Let's try to calculate the omega naught. Okay. So we know this condition has to be satisfied. So actually pi minus 3 tan inverse omega over omega p. That is the phase added by each one of these at any frequency omega naught, right? And this we want it to be 2 pi. Is that clear to everyone? Yeah, that's okay. Yeah. Okay. So you get omega naught to be root 3 times, because pi by 3, right? Pi by 3 is what? Root 3 over 2 and then, right, half. So it will give you root 3. Okay. And you have the second condition, this 1. That's your second condition. Now mod of the denominator is right, mod of the denominator of each stage is root of 1 plus omega naught over omega p the whole squared, and then whole cubed of that, that's all. Okay. And let's put in the condition omega naught is root 3 times omega p. So you get so this is your condition for oscillation, right, from the Barkhausen criterion. Okay. So now what happens if you design A naught not equal to 2? What will happen? Are you sure?
A not greater than 2 it might.
Why?
Things are linear, then it is.
If what is linear?
If system is linear, then it will not. But if it is like non-linear, then it may happen that after some time it saturates again.
What will saturate?
Like because of.
Okay, so let's take the case of A naught greater than 2. Okay, so let's take the case of A naught less than 2. That's simpler. What happens when A naught less than 2? It won't oscillate. Okay. So let's take A naught greater than 2. What happens? Okay, increasing oscillations. Okay, yes. So what happens is your condition for oscillation is satisfied in the sense the omega naught equals root 3 times omega p in this case is satisfied. The phase criterion is satisfied. Okay, so you will have oscillations, except the amplitude will keep growing because you have larger loop gain. So you are feeding back more than what is required. Okay, so now the amplitude keeps growing. Yes.
Yes, and like when we say like amplitude kept on growing, so there we are assuming that there is some delay in the path, because we are saying that something is coming back, then we are assuming delay. But if I see the transfer function, their term is 1 minus h of s.
Yes.
Right, so that will not be, means that term will not be true if h of s is any value other than 2.
Of course.
Right?
So definitely, if you have some feedback delay, you have to take that into account in your transfer function. Definitely.
No, so my question is, if I just see the transfer function, I
Mhm.
will never be satisfied that it will oscillate for h of s more than 2 or a not equal to, because h of s will not be equal to 1 at that point. So if it is not equal to 1, then
No. If it is not equal to, okay. So if you need to do that, if you need to do that analysis, you'll have to look at the poles and zeros of the system and see exactly. You'll have to draw a root locus plot. Okay. We will see if today we'll look at some very basic stuff and we'll see if that satisfies you. If not, we can talk after class and you can ask me. Okay.
K greater than 0 will solve the right answer.
Yes, that's right.
at least simply seeing this criteria will not work. Means,
Yeah, which is why we said it's a necessary but not sufficient condition, right?
This works for all pole system. For all pole system, it is in this.
Yes, that's right. Okay. Okay. And if you just take the case of a, I'm sure everybody knows this, right? If you take the simple case of a ring oscillator, right? Okay, so if you take the case of a ring oscillator, so you know that, so your delay is TR plus TF over 2. You have a rise time and a fall time for each inverter. Okay, and your overall time period is going to be 6 tau. Okay, So in each case, your one of the inverters is going to be either rising or falling, and in one period, each one will rise and fall once. And in general, if you have n inverters, you'll have 2n tau. Will be the total time period, and you can find the frequency of oscillation based on this. Okay. Okay. The other kind of, so we looked at the feedback model, right? The other kind of model which is very useful is to use what is called a one port model. Okay. So the basic idea is you tend to think of, so let's say, so you have a resonator which is an LC tank. And it's connected to an active circuit, right? So the resonator has some resistance Rp, overall resistance Rp, okay? And the active circuit has some resistance R1, okay? So what are the, so Rp basically stands for the losses in the LC tank. So that is what is going to cause your energy to dissipate, right? Yeah, if you create R1 equals minus Rp, then your overall dissipation, power dissipation in Rp is taken care of by the active circuit. Is that clear? Okay. And if you remember, we kept stressing that inductors and capacitors are not ideal, right? So what you'll do is you're going to replace all of these by some equivalent Rp. So that's effectively what we have done here. Okay, over a narrow band of frequencies, this is definitely valid. Actually, let's use Y. So in general, if you have an LC network, it's going to have a real portion and an imaginary portion. Okay. So let's say these are the, okay. So conditions for oscillation would become, so that is the same as your R1 equals minus Rp, okay. Okay. The other condition would be BA plus BF is 0. And this would usually make sure that actually this is what will give you your frequency of oscillation. This condition BA plus BF is 0 is what gives you omega naught. Okay, and the first one tells you whether it's tells you the amplitude in some sense. Okay, we'll see how it tells you the amplitude. So what you'll see is you'll normally require something called startup gain. Okay, which is usually greater than 1. And quite often people use something like 3, a loop gain of 3, but that depends on your design. Okay, so now you have given your loop gain greater than 1. So what happens is your amplitude keeps growing. Okay, at some point of time, what will happen is, because of large signal effects, your actual loop gain actually reduces, because so what you will see is fundamentally all of these oscillators, especially all of these kind of RF oscillators, rely on some kind of nonlinearity. They are actually in very nonlinear systems, and you are using the nonlinearity to limit the amplitude. Okay. Oh. Okay. Okay, let's study this one port view a little bit further. So let's say the voltage across this RLC network is V of t. Let's also assume there is some initial voltage across the capacitor, okay, which is V naught. Okay, what is the Q of this guy? Right, we know this, right? You can write the second order. So you have an RLC network, you can write the second order equation for this RLC network. You can find out the roots of the system. Okay, what you will find is initially the roots lie on the x-axis. Okay, but if your Q is greater than half, what you will find is the roots end up splitting into two such that they no longer lie on the x-axis, but they are two complex conjugate poles. Okay, and what you will find is this system will end up having a sinusoidal component, and if depending on this value of R, it will have an exponential decay. Okay. Yes, well, severely underdamped in the sense it depends on the value of R, like I said, right? So it will go something like this. And this is V naught e power minus t by RC, the envelope of the decaying sinusoid. Okay, the time constant is 1 over RC, right? As R tends to infinity, tau tends to 0, okay, which means the oscillations are completely stable, okay, their envelope doesn't decay at all. So, and obviously you know this corresponds to an ideal LC tank, right, and you already know that. So the energy keeps sloshing around back and forth between the inductor and the capacitor. Okay. Okay, so let's take the active circuit. Oops, sorry. Let's take the active circuit which has some input impedance minus RA. Okay. So again you can represent it as an RLC tank with some equivalent resistance across it. And the equivalent resistance is going to be RRA by RA minus R. Right? Is that obvious to everyone? Okay. So now the envelope will be V naught e power minus T by R equivalent times C, right? Obviously R equals R naught means you have sustained oscillations. R less than R naught. Okay. Oh, RA, sorry. Did I say R naught? RA. Okay. It's a decaying exponential. Yes. Look at this. If R is less than RA, this R equivalent is positive, right? Which means you have an e power minus T by RC form. Okay. Is that clear? So what happens is, if you actually look at the finally you want to be somewhere here. You want the two systems to be somewhere here, right? The two complex conjugate poles. Plus or minus j omega naught. So what happens is, so initially the poles start off somewhere here in these two places, right? One of them is a capacitor, other is an inductor. Okay. Eventually they will move somewhere here. Okay. And you will see them splitting at some frequency. Actually, so this not at some frequency. This is your Q equals half point. That is a point where, so you know, if you take your discriminant and root of b square minus 4ac, you will find that at that point it goes negative, and you can get this condition Q equals half from there. Okay. So if your z of j omega is actually is right in S form. So z of s for this system is SL over LCS squared plus L over RS plus 1. Okay. So you can plot mod z and angle of z. Okay, this is going to be omega naught, and this value is r, that's your peak value of z. Okay, you can define the r over root 2 point, which would give you your 3 dB bandwidth, right? That's your omega naught over q. Remember this. Then you can plot your angle. Starts off at plus 90. Okay, at omega naught goes to 0 because it becomes purely resistive. And this will be minus 45 degrees. Okay, and you know that the frequency of oscillation, neglect all other capacitors, is going to be 1 over root LC. Okay, okay. So let's take this RLC network. We'll add the active portion. Okay, let's try this guy first. Let's try a single transistor RLC. So you have some V0 and the current through the transistor ID. So we will replace it by the equivalent circuit, let's say the feedback model in this case. Okay, minus 1 over Gm is the forward transfer function. Oh, sorry. Right, and this is V0. Okay, at resonance, what is angle of Z of j omega? It's 0 because it's purely resistive. Okay, okay. So your total phase shift is only 180 degrees. Okay, that is from the DC feedback of this guy. Correct? Okay. So this definitely will not oscillate, by the way. Right? So what we'll do is, we'll cascade two of these stages. Okay? Because if you cascade it, you will get 360 degree phase shift. Okay, if you do this, you will get a 360 degree phase shift at resonance. And of course, the loop gain at resonance is defined purely by Gm times Rp whole squared if they are identical. Right? At omega naught equals Rc, 1 over root Lc again. So that the first one, omega naught equals 1 by Lc, 360 degree phase shift, takes care of the angle, okay, the phase portion. The magnitude portion, GMR the whole squared, should be greater than or equal to 1. The greater than comes from startup conditions. Okay, the equal to 1 comes from your basic condition for oscillation. Okay. Okay, now you can redraw this guy into the more traditional form. Sorry. This you might have seen in many places, this kind of, it's just a redrawing of the same thing. What I've done is I've removed the inherent R. You can just assume L and C are non-ideal, there's an inherent R, but I've redrawn pretty much the same thing. Okay, I've just taken this guy and redrawn it slightly differently, that's all. Okay, and this is pretty much, you could say, the basis for most RF on-chip oscillators, on-chip VCOs. So most of them follow some kind of, some form of the circuit. Okay. Okay, so we'll stop here. Next class we'll take a look at the circuit and different forms of the circuit. Okay, then we'll move on to other RF oscillators. So we also have, so this is called the cross coupled oscillator, and you can see why. So you're basically, so the two outputs are here and you're cross coupling it back to the MOSFETs. Okay, so this is called the cross coupled oscillator. Okay, and it's by far the most common RF VCO for on-chip applications. And you also have other kinds which we'll look at, so which are more, so this, what we'll see is this particular oscillator is very amenable to analysis through the one port view. Okay, and we'll also look at other kind of feedback oscillators. Okay, namely the Colpitt's oscillator. Okay, and we'll just, maybe mention the other kinds of oscillators. There are Hartley's, Clap, there are several kinds using different kinds of feedback. So we'll just quickly look at all of those. Okay, all that will be next class. Okay.